Hello, good morning. Today we will discuss about dielectric materials. So first we will discuss about what is dielectric material and what is the difference between dielectric material and other types of materials. Then we will discuss about some of the important points, important definitions related to dielectric materials. Then we will see the types of dielectric material, and at the end we will discuss about the applications of dielectric materials. So dielectric materials are mainly insulators. They are having sufficiently high band gaps. So they will be treated as a bad conductor. But among these bad conductors, there are special characters of certain material. They are forming different dipoles. Due to this dipoles, two polarity, this type of materials are known as dielectric materials. So the first point we need to discuss is the comparison between dielectric materials and conductors. So it's basically a comparison between good conductor and bad conductor materials. But here we are not considering all the bad conductors, we are considering a special type of bad conductors. These are dielectric materials. So like all other bad conducting materials, they are not containing free electrons, or very less number of free electrons are there. Or obviously in case of conductor, in case of good conductor, there will be large number of free electrons are available. All electrons are tightly bound, so that's why we don't have free electrons in case of dielectric material, but obviously it's not happening in case of conductor. So you have free electrons over there. Conduction band is empty, the band gap is sufficiently high, so this is the effect. Conduction band is empty, so less number of electrons are able to conduct, so less current will be observed in the circuit. Charge given in this is localized, and electrons take to and fro motion to leave the vicinity of the atom. So that means they are forming the dipoles inside the system. Dielectric material, in that sense, they don't conduct electricity. Actually, the electricity is conducted in terms of free electron, the movement of free electrons or movement of free charges. But here there will be some type of electricity, some type of electric field will be there, but this is not due to free electrons. But obviously in case of conductor, there will be electricity, the free electrons are moving, applied small potential, electrons will move. For a particular applied field strength, dielectric losses in insulation character, in this minimum field strength is called the breakdown strength. And obviously as they are good conductor, high conductivity is there, so there is no concept of breakdown strength. Some of the simple examples are there: mica, glass, plastic. You can get number of examples of dielectric material. We'll come to this point. And obviously the conductors, mainly the metals having large free charges. Now our next point is to comparison between insulators and dielectric materials. Obviously the name insulators is also bad conductors. Actually both are bad conductors, but depending on their applications, we are separating insulators and dielectric materials. Now in case of dielectric material, the material in which an electric field can develop with the minimum loss of energy is known as dielectric. Whereas, just let me get this, the substance which have low conductivity and which create obstruction in flow in current is known as insulation. So a basic difference between dielectric and insulator is that, so it will go to stop the whole amount of current inside this thing, but in dielectric there will be small electricity will be there. A loss due to this thing material, the loss will be very, very minimum. Something will be observed there. It's a bad conductor, but you will get some amount of electricity, some amount of electric field will be there. Now the most important part is that they are polarizable. So when electric field is applied, so this material will give you some polarization in the system. But obviously insulator, there will be no polarization. In case of insulator, so conduction band is obviously very less number of electrons, less number of free charges are available. So a sufficiently large bonding is there, so that electrons cannot overcome this bond, so less free charges are there. But here the bond is relatively weaker. it's stronger than metal but relatively weaker than the insulated. So you have free chances of some movement. Obviously dielectric constant is high and this is low. We'll come to this point, what is the meaning of dielectric constant. It's obviously source charges. This is depending on their application. We need to talk about this one. Some examples are there. Obviously dielectric examples we have considered. So you will get another examples also. Obviously the air, if you don't have moisture or less moisture, so they will act as a dielectric material. And vacuum is also a very, very good dielectric material, and distilled water. And obviously these are also bad conductor, the plastic, cotton, mica. So they are insulator, but sometimes they can be used as a dielectric materials. Applications: capacitor, obviously power cable. So you can use this one. So we'll come to this point, what are the applications of the dielectric materials. Now here, depending on their application, means the conducting wire, insulation. So you know, if you have a metal wire, so this metal wire carrying a large current through this, so there is a high chances of electric shocking. So to get rid of this thing, so you used to put some jacket over there. So this jacket is basically made of a insulating material. So this insulating material is a bad conducting material. So through this red section, through this red wire, current will pass, but through the blue region, so there will be no current. This is the advantage of the insulating materials. Now there are two types of dielectric material. One is called the non-polar dielectric material and another is called the polar dielectric material. So the idea is that, so when you apply electric field, the atoms or the molecules, they are forming dipoles. But there are two types of dipoles available. There will be permanent dipoles, and in another case, if you apply the field, the atoms or the molecules, they are forming dipoles. Okay, they are not permanent. So there are two cases. In one case you have permanent dipole, in another case you have non-permanent dipole. This is the example. This is the difference between polar and non-polar. So polar means you have a permanent dipole in the material. Even if you are not applying any external field, so there will be always dipole dipoles inside the material. Whereas in case of non-polar dielectric material, so normally they don't have dipoles, but as you are applying the external field, so the atoms or the molecules, they are forming dipoles. So examples, the common example for non-polar molecules are CO2, oxygen, nitrogen, hydrogen. These are the examples. Whereas the polar, HCl, H2O, these are the examples of the polar materials. Now come to this point, a comparison between these two. So you have permanent and you have a induced if you are applying this one. So the polarization is temperature dependent, and here this is temperature independent. But the most important part is that in case of polar dielectric material, when you have nucleus and surrounding this there will be electrons. So in case of polar materials, obviously they are not coinciding with each other. But in case of non-polar, the electrons and the nucleus, they are exactly coinciding with each other initially. But as we apply the field, they will shift this one. So say somewhere here you will have your nucleus and the shape of the electron cell will be something like this. There is some changes. So the center of gravity is changing. So here center of gravity was almost coinciding with each other, but here this is not exactly coinciding with, this will be somewhere here. But in case of non-polar, so obviously as they have permanent dipole, they are not coinciding with each other. Their center of gravity will be somewhere here. Now the most important thing, the types of dielectric materials. There are three types of, obviously for three states available in normal engineering sciences. One is solid, liquid and gaseous. So the solid, we have just mentioned this one, there will be polar and non-polar type of things. So the solid, there are possibility that there will be simple elements. They will behave as a dielectric materials. There may be non-polar dielectric material, there may be polar dielectric material. Okay, so you have a set of examples are there. So obviously the sulfur, mica, germanium, they will act as a dielectric material. Same way the non-polar, so high density polyethylene, polystyrene, they will act as a dielectric material, a non-polar dielectric material. Okay, rock salt, C6H5NO2, they will act as a polar dielectric material. Whereas liquid, so you all know about liquids, there are mineral oils, they will be acting as a dielectric material. One of the important thing for different applications, electric application, the transformer oil, the capacitor oil, okay, the silicon liquids, they are very good liquid dielectric materials. Okay, so in number of electrical cases we need to use this one. And the gaseous one. Okay, the easiest way to use any material as a dielectric material, this is air. So take some air and put something, this thing within two conducting plates. This will act as a dielectric material. Okay, so there are some hydrogen, nitrogen, HF6, they will act as a dielectric materials. Now this is idea about dielectric materials, types of dielectric materials, some comparisons and some examples. Now come with some of the important definition. So you know about electric flux, so the by definition, so you know electric lines of forces. So if you are considering some unit cross-sectional area, just consider a unit cross-sectional area. If you are considering circular area, so your calculation will be much more easier. So if you have a charge somewhere here, okay, so from this charge some number of lines of forces are passing, okay, they are coming from this one. So the question is, through this unit cross-sectional area, how many number of lines of forces are passing? This is the calculation of flux. If you are able to calculate what is flux, if you just multiply this thing with the volume or other cross-sectional area, so you will get the total number of the field inside the system. So this is the importance of electric flux. Get the flux for unit cross-sectional area multiplied with the total volume or the total surface, you will get the total amount, idea about the total amount of charge. There is another important part. This is known as electric displacement vector. So this displacement term comes with dielectric material. This is not the effect of other materials related to electric things. So when you have a dielectric material, there will be displacement. Now in simple way, what is the meaning of this displacement? So if you have a dielectric material, okay, so you have already mentioned this thing, the dielectric materials are forming dipoles. Whether we are applying the field or we are not, they have a permanent field, but they are at some dipoles. Dipole means in one side you have a positive side charge, another side you have a negative charge. And this positive charge and negative charges, they are separated by a distance. Okay, so I'm just assuming this is positive charge and this side is negative charge. Okay, now if you just applied the field, okay, so say if this is positive charge, if this is negative charge, so obviously this positive and this positive, they will go to repel this one. So they will try to change its position from this direction to this direction. So due to that applied field, the polarity of this dipole will be reversed. So now the negative will come somewhere here and positive will be shifted towards this. Okay. Same way, if you change this one, if you make it negative and if you make it positive, obviously this will be this one. So they have some displacement of this one. Say a displacement of this dipole. Although they are not exactly rotating 180 degree, there will be small rotation, but still you can think about there will be effect of some attraction. This attraction gives you some field in the system, and this is related to electric displacement field. Okay, so obviously you can think about the lines of forces are there due to this positive charge and negative charge. There will be some lines of forces, and for the unit cross-sectional area, how many number of lines of forces are passing? This is the calculation of this flux. Permittivity. Permittivity defined as the ratio of electric displacement vector D in a dielectric medium to the applied electric field strength. So it's simply a ratio between, we are talking about dielectric material, it's simply, let me just take a different color. So we are representing it by D divided by E. So what is E? They are vector, obviously, they are vector quantities. E is the electric field, applied electric field, and this is the displacement field. Okay, so the ratio will give you permittivity in the system, epsilon. Now we are talking about displacement field, we are talking about displacement current in the system. So obviously displacement current is due to the dipoles. This is due to dipoles. So what is dipole? Now this is dipole. Positive charge, negative charge, they are separated. So the dipole moment is given a charge into distance, and obviously the direction will be given according to the field, that means along the positive charge. Now the meaning of polarization, what we have just explained, that if you have two conducting plate, inside this thing there is some dielectric material, so the dipole is keep on changing its orientation. That means one side is positive, another side is negative. So we know the lines of forces or the electric field lines, they starting from positive moving towards negative. So the direction of the electric field is in this direction. Okay. Now if we change the polarity, so obviously this will be positive and this will be negative. So the polarity is changing. Okay. So the orientation of the dipole is different. So this is the idea about polarization. Now dielectric constant. So what is dielectric constant? So in simple way, dielectric constant or relative permittivity, sometimes it's called the dielectric constant, we call the relative permittivity of a material, determines its dielectric characteristics. Is the ratio of the permittivity of the medium and the permittivity of the free space in a dimensionless quantity, is a dimensionless quantity. So either you can represent it by kappa or you can represent it by epsilon r. Okay, so we need to talk about it's a relative one, r denotes the relative one. So now you have the relative permittivity, that particular material, and in comparison to you have the vacuum one. Okay, now one of the important part is polarizability. Now when you talk about polarizability, it's a simple word, it's a simple addition of polarization and ability. So we're just adding two words. So ability to be polarized. We are applying external field, so the atoms or the molecules, they are forming the dipoles. So this is the idea about polarizability. So when you have two atoms placed side by side, okay, you have positive charge and negative charge, there will be another positive charge, that means the nucleus, and electrons are surrounding this one. So if they are free, they can easily be polarized. But as the material inside the bulk material, so they are not free, they are connected with each other. So when you are applying the field, obviously this positive charge, they are interacting. The positive charge and the negative electrons, they are interacting. So there will be electron-electron interaction. This is also there. So this stops to be forming, to form the dipoles. Okay. So to be polarized, or the ability to be polarized, it purely depends on the material. So which type of atomic bondings are there, which type of arrangement of atoms are there, the structure of the unit cell is there. This defines how they will be polarized. The polarizability is explained by this. So it's a dipole moment, it's proportional to applied electric field. The proportionality constant is alpha, which is known as polarizability. Now the susceptibility, a susceptibility is proportional, okay, or you can just say that this is the polarization vector P. I'm just writing polarization vector. Now you know due to that the formation of dipole, they are changing their orientation, so there will be certain field. So that external field, not external, that internal field due to the external field is known as polarization. The polarization field is proportional to the applied field. Obviously the applied field plays the role. The applied field forms the dipole, applied field forms the polarization. So they are proportional. And the proportionality constant is known as susceptibility. Obviously, remember this one, that individual dipole is also proportional to the applied field. So the total polarization, what is the meaning of total polarization? Total polarization is total number of dipoles inside the dielectric material. So in simple way, P, capital P, in simple definition, classical definition one can give you, this is N into mu. What is mu? Mu is the dipole moment, individual moment, and N is the number of dipoles. So this is the idea. Okay. So if mu is proportional to E, obviously P is also proportional to E. As we know, the N is constant for a particular medium. So just rearranging this one, and we got the relation between the dielectric constant and the susceptibility material. So susceptibility is given as epsilon r minus 1, dielectric constant minus 1. Now, as you have talked about two atoms placed side by side, actually there is not only two atoms, there will be atoms surrounding this one, there will be large number of atoms in all the directions, all the three directions. So there will be interaction between the atoms, interaction between the dipoles also. So there will be the effect of individual atoms on them, and along with this, the electric field inside the material, electric field inside this dielectric material, where you have number of dipoles. Okay, say this is the form of dipoles. Okay, there will be number of dipoles are there. So obviously, say one side is positive, another side is negative. They are orienting in another direction. So this is positive, this is negative. So just to remember, this positive and this negative, they will interact. This positive and this negative will interact. There will be other atom in this side, in the back side of this one. So there will be interaction between this. So obviously this will produce a local field inside the system. There will be some sort of local field there, which is not due to the external field. This is due to the charges of the dipoles, charges of the atom. So this is denoted by the local field of a three-dimensional solid materials. Obviously for the gaseous or the liquid, this interaction is quite less. So the local field is almost absent. It's negligibly small, you can consider. But in case of solid material, the local field is sufficiently large. So that's why it is observed that the local field is the effect of external field plus P divided by 3 epsilon 0. So 1/3 of the polarization is also included in the local field region. So obviously you are applying some field here. Now here, somewhere here, the field increases. The field becomes P plus some delta E. E plus some delta E. And what is the delta E? Delta E is given as 1/3 of P. What is P? P is the polarization. So if you just rearranging those equations, you will get one of the famous equation which is known as Clausius-Moschotti equation. So this is mainly applicable for the solid materials. Just rearranging the terms and you can get this expression. Now these are the important definitions related to dielectric material. Now we'll come to the important point of types of dielectric material. Types of polarization rather. So the polarization, there are mainly 4 types of polarizations are there. First one is electronic polarization, second one is orientation polarization, third one is ionic polarization, and the fourth one is space charge polarization. Let me just describe it in a simple way. Electronic polarization, they are basically forming dipoles from the atoms. Now you can see the atoms where the center of gravity, they are coinciding with each other. When external field is 0, so the polarization field is also 0. But as you have applied the field in one particular direction, so there is the formation of dipole. This forms a polarization. This is known as electronic polarization case. Orientation means they have permanent dipole. Now see, E is 0, P is 0, but you have some dipoles in one direction, but they are in random direction. So their net polarization is 0. The net polarization is 0. But as you have applied the field, now they are orienting in a particular direction. So they have some polarization in a particular direction. So P is not equal to 0. We have certain polarization. Now ionic polarization is obviously applicable for the ionic material. When you have positive and negative, cation and anions. So the cation and anions, they are placed positive and negative. Apply the field. Okay, when electric field is 0, so P is obviously 0. They are in a particular direction. They are in a proper arranged manner. But apply the field, now the positive and negative, they will be shifted in a particular direction. So P is not equal to 0. You have certain polarization. So obviously when you have some polarization, so you will have the effect of the dielectric thing. Ionic polarization. Now the case of space charge polarization or accumulation polarization. So what happens? In this case you have certain clusters, certain zone. When you have one side is positively charged, another side is negatively charged. This is because of the solid materials. Solid material cooled at different temperature or uneven cooling gives you this type of pattern. Inside the material there will be cluster, there will be certain zone where you have positive and negative charges. They are random initially. When the field is 0, polarization is also 0. But apply the field, they will be orienting in a particular direction. So polarization will present there. So when you have polarization, obviously they will act as a dielectric material. Okay. So change the orientation, polarization will be reversed. And this thing will give you the field in the material. So these are the comparison between different polarizing materials. So electronic polarization, deformation of electronic cell, that's mean the atoms. Atomic or ionic polarization obviously related to positive and negative ions. Okay. Dipolar or orientation polarization, it's because of dipolar molecule in liquid. One of the simplest example is water. Space charge occurs when the charge is accumulated at interfaces. Composite materials, and one of the examples are composite materials. Again, we have some simple comparison. The examples are mainly, you have already mentioned this thing, in which cases we will get different types of polarization. They are mainly inert gases, although some other examples are there. Ionic crystals are there. So these are, in this case, they are ionic crystals. Okay. The alcohol, methane, they will have the orientation, mainly the organic materials. And space charge, the solid material, the semiconducting material, the ferrites. So temperature dependency, so they are almost temperature independent. Obviously for a certain range they are temperature independent for a wide zone. And here they are temperature, even if you are talking about a particular temperature range, they are purely temperature dependent thing. But the most important part is relaxation time. Now what is the relaxation time? So if you apply the field, they will have a polarization. Now remove the field, just remove the, switch it off. So they will come back to its initial position. So in this case the relaxation time is very, very fast for this electronic polarization. But others are slower. You can see the space charge polarization, they are the slowest one. Power loss, this is minimum as we are directly interacting with the atoms. So this is minimum, but as we move with the dipoles and the total cluster, the losses will be very, very large. The frequency range, this is given, obviously here we need the frequency range, this will be higher, okay, and here the frequency range is the minimum one. And the relation, okay, the polarizability, I have just mentioned what is the polarizability. Now one of the question is how to calculate polarizability. Now to explain polarizability, we will take an example of one of the particular case. For other cases, you have the same thing which will be repeated for the different charges, different types of charges. Let me just check it. So to do these things, we have taken the electronic polarization. So what is there in electronic polarization? Nucleus, electrons, apply the field, they are forming dipoles. Now initially center of gravity was coinciding, but then after that center of gravity is not coinciding. So one can get the charges. So we are considering Z number of protons are there. So we have Ze charges in the nucleus and minus Zd are charges in the electrons. So we have a homogeneous distribution. Obviously the dimension is very less. So we are assuming they are obviously having a homogeneous distribution. Volume, as we are considering, it's a spherical one. So this is 4/3 pi r cube. Now what is charge density? So charge density we can simply written as, sorry, let me just take it a different color. Charge density is total amount of charge divided by volume. Okay, volume is 4/3 pi r cube, and charge, this is obviously Z into E. Okay, so we have just simple rearrangement of this one, Z and the C was taken over there. Now come the case of forces. As we have applied the field, obviously the forces will be there. So initially force was balancing each other, there is no problem. Now the force is electric charge into electric field. So Q into electric field. What is Q? Q is equal to Z into E. Into electric field. This is the charge. So initially this was the equation. But what happens as you have applied the field? Something is changing. So obviously the force values will be different over there. Considering that the shape is not disturbed at all, although in this particular picture it is shown that the shape is totally disturbed and it becomes elliptical one. So we are assuming there are two forces which are balancing each other. Okay, so which type of forces? The Coulombic forces in this direction, and obviously the formation of dipole gives you another force because of the redistribution of charges. So let me just calculate the force. The initial force is because of J into E. Okay, so this is the force which is balancing, which is holding the atom. And due to the external electric field, the new force will be generated. So new force is because of the new volume. What is new volume? Because of the shape change of the atom, shape change of the dipole. So this will be different. If this is different, so obviously the charge will be different. If charge different, then the charge density and the whole thing will be different. So one can calculate new force from this one. It's the same concept, but charge density will be same. Now in both cases charge density will be same, but here this will be different. We have new charge and something new volume will be there. I am writing it N. Okay, so in that sense actually charge is not really changing. So charge is same, total amount of charge is same, total amount of charge is same, but the volume will be different. As volume is different, so the charge density, to make it constant, so charge will be modified up to a certain level. This will be distributed. So if this is happening, so the force, so new force will be generated because of this spreading of, because of the formation of the dipole. So now we need to equate these two forces. Obviously they must balance each other, then only there will be existence of this atom, otherwise they will come out, there will be blast of this thing. If you are able to do these things, you will be able to calculate what is the total dipole moment in the system. If you are able to calculate what is the dipole moment, so now you know what is the dipole moment. So if you know dipole moment, you can get what is the total polarization. If mu is known, dipole moment, so multiplied with n, this will give you the total polarization. If you know the total polarization, so you can calculate what is susceptibility in the system. Susceptibility is P divided by the external field. Sorry. And also you will be able to calculate what is polarizability. Remember what is polarizability? Polarizability is mu is proportional to E, and the proportionality constant, this is equal to alpha, the polarizability. Okay, so one can easily calculate this. This is the case of electronic polarization. This will be applicable for ionic polarization, this will be applicable for ODN polarization, and this is also applicable for the space charge polarization. Concept of calculation will be same. You need to calculate the forces, you need to calculate the balancing forces, and then from that you can get what is R, the distance between the dipole, or the modified distance between this. What is this distance we are talking about? We are talking about this particular distance. You need to get that R. If you get R, you will get mu, then P, then susceptibility, and also polarizability. You can calculate. You will have all the information. This is summarized over there. So we are not calculating this one, but you know how to calculate this thing. The procedure is known. So the last part, the last particular part is the application field. So obviously one of the important or the simplest case or the most used case is in case of dielectric material. Take two metal plates, put the dielectric material, this will act as a capacitor. And you know use of capacitors. Number of cases capacitors are used. RLC circuits. In RLC, a capacitor plays a very, very important role. Okay. In number of cases, capacitor, in power electronics, capacitor, some of the cases capacitor can be used. In case of filters, okay, we can use capacitors. Sometimes capacitor can be used as a switching device also. Now the insulation. Okay, obviously for a high tension line or the cables, we can use the insulators. Okay, and the transformer oils, they can be used. So simultaneously these are used as an insulator, and also it's acting as a dielectric materials. dielectrics are used for the mechanical support for the high tension lines. Okay, so you have all seen that high tension lines with a gap and long wires are there, they're connecting with each other. So this gives the mechanical support in the system. So you have this high tension line examples. Now one of the important thing is the microwave ovens. They are basically used for that dielectric heating. So what is the idea of the dielectric heating? If you have a food, okay, it will contain some water molecule. Okay, so now when you put this thing inside the oven, switch it on, so microwaves are coming. So microwaves directly passing through this material and interacting with the water molecule. When they are interacting with the water molecule, they are changing their orientations. Obviously you are using alternative current, they are changing its orientation. This obviously gives you certain amount of heat in the system. Okay, so this is one of the application which is known as the dielectric heating. Okay, this is one of the important, very important one. There is some parts, modern day we are using the capacitors, big capacitors for energy storage devices. Now although we are considering this is as an application, but this is one of the important dielectric material. This is known as ferroelectric material. Example, barium titanate, BaTiO3. Now what is there? This ferroelectric material, they have some dipoles. We can see the crystal structure of this. Okay, now this is the dipole moment direction. Okay, now this type of ferroelectric material can be used for the memory devices. Now as you are using computers, you are using laptops, mobile, there will be some memory devices. Okay, so the ferroelectric materials, they are very reliable materials for this type of things. So you can see a transistor, a MOS transistor, where in the challenge region the ferroelectric materials were used. Just this above this one you have this ferroelectric, you have this challenge one, and here somewhere here you have this ferroelectric material. So ferroelectric material is obviously acting as a two-phase thing. So one will be switching on, another will be switching off. So obviously the memory device is using binary concept. The ferroelectric material helps us to achieve this thing. Okay, so it's a non-volatile memory devices can be used by high capacitance value of this ferroelectric materials. Okay, thank you.